Hi guys, so today I'm doing our final lecture for this unit, and this is actually going to be our final new unit of the school year. Due to the digital and remote learning and how the AP has edited the material covered in the exam, this is actually the last unit of new material, and then we just do review up until the AP test, which is now May 14th. After that, just stay tuned. So, Gibbs and equilibrium. We've talked about Gibbs free energy. We've talked about what a good delta G is and what a bad delta G is, aka negative and positive. And that this is just review for us at this point, that if a reaction we want to go towards the products, Gibbs must be negative. However, if we want it to not favor the product and favor the reactants, aka not go in the normal direction we're used to seeing, that would be when Gibbs is positive. Gibbs positive is going to favor the reactant side. And we're kind of using this language to talk about it now to segue into our understanding of equilibrium. So, what happens when our reaction's at equilibrium? Of course, delta G would be zero, right? Because at equilibrium, we're at that sweet spot where it's settled into where it wants to be. Now, we actually have an equation that relates delta G to what we understand mathematically about equilibrium, which is an equilibrium constant, okay? So it's right here on that screen, the delta G equals negative RT ln of K. So R is a different value from the one that we use with our ideal gas equation. So this one is in joules per mole Kelvin, and it's 8.31. Your temperature, of course, is going to be in Kelvin. Delta G, remember, when we calculate or we usually compare it to data, or if you're given a delta G, it's usually going to be in kilojoules per mole. The reason I'm highlighting this is because your R is in joules, not kilojoules. So if you were asked to calculate delta G and report it out in kilojoules per mole, your final step after using this equation would be dividing by 1,000. On the flip side, if you're given a delta G, it's going to be in kilojoules per mole. And plugging it into this equation, you first have to convert it into joules per mole by multiplying by 1,000. Okay, here's an example problem. I'm not going to do them out, but I will talk through how to go through them and how you would approach this. So very often, that equation would not be used in a vacuum in AP, meaning you're not just given all the numbers and plug and chug. There's usually something you'd have to do before you could use the equation and plug and chug. So in this case, you're given the standard state free energies of formation for an equation for the acid dissociation of H2CO2, which is formic acid. And it says to use that formation data to calculate the acid dissociation equilibrium constant, Ka, for that acid, okay? All you would do here, and I kind of have it written out, but I wanted to talk through it. Last lecture and problem set, you were taught how to calculate delta G for a reaction using the G's of formation for all the different substances, right? It's just products minus reactants. So you'd be able to calculate delta G by using the product G's of formation, right? That negative 351.0 plus 0 minus that negative 372.3, because that value is for the reactants, to get your delta G. Once you have your delta G, then you can plug into that delta G equals negative RT ln of K to calculate K, because it's left ambiguous on purpose. You can use that equation to calculate a Ka or any Kc, right? Kb, Ksp, or a Kp, right? Kps would be using partial pressures at equilibrium if there's gases in the reaction. But once you've used, in this problem, your G's of formation to get your delta G, then it's just plugging and chugging, putting that value in for delta G, your 8.31 for R, your 298 for T, and I know it's 298 because these are all at, with that little circle, standard state, which is 298 Kelvin. Okay, another example here if you noticed, you're given equilibrium partial pressures. So this would be an example of, instead of using a Kc value of some sort, you're using a Kp. And here you're asked to calculate G rather than K. Now, again, there's an extra step you'd have to do before going right into that delta G equals negative RT ln of K equation, okay? You're given your temperature, which is 298. You can plug that right in. Of course, we always know our R is 8.31. However, we have to do a little legwork to calculate our K value, because you're not given your K outright, you're given your equilibrium partial pressures. But we know how to write a Kp expression for this, right? It would be our products over our reactants. So my Kp I could easily calculate by doing my equilibrium partial pressure of N2O4 as the numerator, right? Because it's products over reactants, divided by my equilibrium partial pressure of NO2 squared, because of that balancing coefficient of 2. So I'd be able to do the 0.505 divided by 0.953 squared in order to get my Kp, in order to plug in. So my delta G equals negative RT ln of K. Now, what if you're not at standard conditions? Easy. Remember, what's not standard conditions when we're looking at equilibrium is not equilibrium concentrations or not equilibrium partial pressures. However, we use that same format of products over reactants, but instead of calling it K, we call it Q, okay? So in that case, we would almost always know we'd be able to find our delta G at standard state, okay? We'd be able to use that using that table that I've been linking with every problem set that lists all of your thermodynamic data on it that you would need. You could use your G's of formation to get that delta G at standard state. R, again, is still that 8.314. T is still your temperature. And then instead of K, this equation allows you to plug in Q, aka your partial pressures at any other given point other than equilibrium, or your concentrations at any other point other than equilibrium. Now, in this problem, you'd be able to plug in, and notice I gave you extra information because this is common in AP problems, right? Think to yourself, do I need to know the grams of S? Of course not, because solids don't go into a Q value or a K expression, either one. So that would be just extra information that you do not need. Now, when you solve a reaction for delta G and you get a negative, right? What does that mean again? The reaction is thermodynamically favored, okay? However, there are plenty of reactions that are thermodynamically favored, can quite frankly have a very large, or a very negative, I should say, delta G value. However, you put the two reactants in your beaker to let it run and nothing happens, right? And you think to yourself, how is this possible? I did all the legwork and it's saying it's thermodynamically favored. Because the reaction's under what we call kinetic control. What does that mean? Okay, a reaction, even though it's thermodynamically favored and the equilibrium should lie heavily to the product side, does not proceed at any rate that we can kind of measure, aka it seems like it's not happening even to us, because maybe it's something that would happen so slowly it'd be hard to kind of quantify. The reason of this is because of kinetics, not because of thermodynamics, okay? In this case, we usually have a very high activation energy. Remember, in order for a reaction to kinetically go reactants to products, it has to overcome that activation energy, right? It has to be energetically enough to do that, okay? And this happens quite frequently, okay? What are some possibilities here, right? This could be a bimolecular or termolecular type of collision scenario in your slow step for this overall reaction that's just not allowing it to overcome its activation energy. Because if you remember back to our kinetic unit, we said that as the more molecules necessary to collide in that slow step meant it was less and less likely to happen, right? Termolecular especially are very unlikely to happen, okay? So a reaction that has a slow step that's termolecular but is thermodynamically favored essentially wouldn't happen not because of equilibrium, not because of thermodynamics, because of kinetic control. And kinetics is completely separate from thermodynamics and equilibrium, right? Thermodynamics and equilibrium are over here and they're very closely tied. Kinetics is its own individual operation and they do not relate to one another. So you could easily be thermodynamically favorable, but not kinetically favorable. Okay. The opposite can be true as well. Okay. We can drive forward a reaction that's not spontaneous. The reality is we just have to put in some kind of an external source to force it to happen. Okay. The first one is electricity. Now, this type of reaction we call electrolysis. We would have done it in our next unit if this had been a normal school year and I would have had to proceed through another unit before the AP test called electrochemistry. But we use essentially electricity in a battery to force a reaction forward that would not usually be a spontaneous or favorable in the forward direction. Right? We can also use a light source to do this as well. We can use UV light is a common one that we can use to force a non-favorable thermodynamic reaction forward. And you guys actually, we see one happen all the time in our daily lives, right? Photosynthesis is incredibly thermodynamically unfavorable. So you see that I have the delta G value on here for the photosynthesis reaction. It's positive 2,880 kilojoules. That is incredibly unfavorable thermodynamically. However, we know from our surroundings that it happens all the time, right? Why? We also know that photosynthesis does not happen without, of course, sunlight, right? Or light of some sort, right? The most natural one being sunlight. That light acts to force that reaction forward, even though it's not thermodynamically favorable on its own. Think about it, right? How many people did science fair projects where at some point in elementary school or middle school or their science teacher did it, where you did the putting the plant in the sunlight versus putting it in the dark closet? In the dark closet one, it didn't grow, it lost its color. Obviously, in the sunlight, it grew and it kept that beautiful, vibrant color. Why? In the closet, it did not have that external energy source to force that thermodynamically unfavorable reaction forward, while putting it in the sunlight, it did. Okay, guys, that is it for our final lecture of any new stuff for the year. I will link this in with your problem set. It is a shorter problem set for this. And then that'll wrap it up for this new information for the unit. I did cut out the POGIL just so that you had a little bit less to worry about and not have an extra added assignment over break. This technically isn't due, this problem set, until whatever your first day, I think it is that Monday of break. So I'm making this problem set due that Sunday night, April 19th, because then your review guide will be your assignment for that Monday, and then your test will be that Wednesday, and that will be your final test of the school year. From here on out, I'll just be assessing you a little bit differently. Have a good one, guys.